And we're basically going to just be working through this. This is like all the materials that we're going to talk about. And there's this really brief, for starters, I think most of you guys met me or we've met at this point, but I'm Nick Wogan. I gave a talk yesterday. I'm here all week. I'm from NASA Ames, and I do photochemistry and climate modeling like a lot of you guys. And yeah, so we're going to talk about photochemistry and climate modeling with some software that me but with the help of many people have put together over the last 3 or 4 years. And we're going to go through this GitHub page here. Though this has got a bunch of tutorials and a very short, brief workshop schedule. So the first thing we're going to do is just we're going to just start at the beginning, and I'm going to just tell you broadly what is photochemical modeling, what is climate modeling. I know a lot of you know this, but we'll just start in the beginning. And then we're going to talk about how to install the photochemical model. And then we're going to do a photochemical model of modern Earth. So we're going to simulate the photochemistry of Earth. And this is going to be like a live demo. So what I envision is that like in each of these folders here. So we're going in chronological order. So who here is familiar with Jupyter notebooks? Okay, great. So in here, there's 2 notebooks. One is like completed. So this is like essentially my notes and where we're trying to go in this live demo. So this has got all sorts of, plots and different things in it, but we're going to be starting with the notebook that doesn't say completed, essentially a blank notebook, and we're going to work our way towards the completed one. So that's the idea. And that's for 3 different projects here. So we got modern Earth photochemistry, then we're going to do a climate tutorial, and then we're going to, hopefully, by doing the modern Earth photochemistry and some climate modeling, then that's going to give us the tools to simulate the climate and photochemistry of TRAPPIST-1e. That's the idea. So yeah, let's, I think it makes sense that probably looks super tiny, that text. But let me just go. If you guys want to find this GitHub page really quick, I'll just go here. Okay. Yeah, there. That's very big and obvious. Oops. Yeah. And let me know if has anybody not found, or yeah, let me know if you found it. Got it. Okay. Has anybody not found it yet? Okay.
Oh, it's just under GitHub.
Yeah, right here. You're good. You're good. That wasn't very explicit. Cool. Good, good to go, Lily, or almost? Yeah. You're fine, you're fine. Good, okay. So we're gonna start intraday photochemical modeling. Okay. And these slides are linked in that GitHub page under one background, photochemistry, climate, or something like that. So yeah, so we're gonna be talking about PhotoChem. That's the name of the software. It's a photochemical and climate model. It's one-dimensional, so the vertical dimension is considered, and we ignore horizontal changes in atmospheres. And yeah, so we're gonna just kind of start from the beginning. So in a nutshell, PhotoChem is a software package that contains a one-dimensional photochemical model capable of simulating a wide range of atmospheres. So rocky planets, mini Neptunes, hot Jupiters. The idea is to have something that's general and can be applied to any world. And the code also contains a 1D climate model for rocky planets and a chemical equilibrium solver. We're not going to talk about the chemical equilibrium solver, but yeah, that's useful for some gas giants. Oh, yeah, and yeah, photochemical and climate models, they predict the chemical composition and temperature structure of planetary atmospheres. And right, I don't need a lot of you guys use these kinds of models, and so obviously they're useful for all sorts of scientific questions, from understanding exoplanet observations to the early Earth atmosphere to also the solar system atmospheres. So I guess just a little survey, who has worked with like photochemistry simulations before? A little bit, yeah. And who's worked with like climate simulations? Nice. Okay. Wonderful. So I'm going to just start from the beginning. A one-dimensional photochemical model, it's just a description of how atmospheric chemistry changes over time from gas transport, chemical reactions, and some other processes. And then in math, we solve this equation, this partial differential equation. And on the left is the rate of change of a species concentration. And it equals vertical transport and also chemical reactions affecting that concentration. And then there could be other processes in the atmosphere like condensation or the effects of lightning or any other sort of source or sink of the gas that you can imagine. And most of the time, we are interested in steady states to this partial differential equation. So, right, if you can have some atmosphere and it may want to evolve over time chemically, and the species will change concentrations because of chemical reactions. But then it will eventually reach a point, well, not necessarily the case, but often it will reach a point where there's a steady state and the atmosphere just stops changing. There's still all sorts of reactions happening in the atmosphere, but no gas is changing concentration. And that's what this little diagram is showing here. You have concentration on the x-axis, altitude on the y-axis, and when the atmosphere is changing, it's not in a steady state, and then eventually it reaches a steady state. And most of the time, we're interested in steady states because most atmospheres are in quasi-steady states, right? Like Earth today, the chemistry more or less is in a steady state with some caveats like climate change. There are slow changes to atmospheres. And this is the general assumption for exoplanets, that they'll be in a quasi-chemical and climate steady state. Oh, yeah. And then as a picture, a 1D photochemical model looks something like this. So here I'm imagining an Earth-like world with an ocean and an atmosphere. And yeah, most of the chemistry is driven by ultraviolet light coming from the star. That starts most things. and then you have subsequent reactions affecting the chemistry. And then there's all sorts of other processes affecting gas concentrations, like vertical mixing and rainout in droplets of water and these sorts of things. Okay, so that was the super fast intro day, photochemical modeling. Now climate modeling. So a climate model it just computes the temperature structure that a one-dimensional climate model computes a temperature structure that balances the radiative and convective energy transport. And if, the equation for climate modeling is pretty simple. It's this partial differential equation here, where you say, okay, the rate of change of temperature is equal to two things, radiative energy and convective energy. And this equation looks mysteriously simple, but it's not. So the hardest part of climate modeling is computing how radiation affects temperature change. So like how much is the sun heating the atmosphere versus how is it cooling via its emission. That is a complicated process mostly because gases just absorb in such a complicated way as a function of wavelength. Convection, also complicated, but in 1D models, we make some crude approximations. Yeah, and we don't have time really to get into the details of this, but a lot of this is described. I mean, I'm sure a lot of you have taken classes like with Ty and Sukrit about these topics and have gone into the details. Also, I've learned a lot of this stuff in my advisor's textbook from 2017. He's got appendices on photochemical and climate modeling, and I think it's a really great textbook for that I refer to all the time to remind myself of these things. Oh shoot, yeah, I didn't know that was there. Let's move that. Oops.
Thank you.
Okay. Oh yeah. And then the appendix of my PhD thesis also goes over photochemical modeling. I start with there's conservation of molecules, and then I work my way all the way till the discretized equations that you implement in a computer. So if you really want to go down the rabbit hole, you can check out the appendix of my PhD thesis. So yeah, PhotoChem is an open source model that solves these equations. It's on GitHub. Anybody can use it. A number of people have used it for various projects. So the code itself is largely written in Fortran, and it's not that terrible old Fortran that we're familiar with our advisor's codes. It is newer Fortran, and it looks a lot like any object-oriented programming language like Python or C++. So I hope it's somewhat understandable. But I never use it via Fortran. There's a Python wrapper to it that uses Cython. So you can, I just use it via Python, and it's great. It's really easy to install. We're going to talk about this in a bit, but it's on CondaForge. And so, when you do conda install numpy or conda install scipy or whatever, you can just do conda install photochem, and it goes on your computer. Oh yeah, the heritage. So of course, all these codes have histories. And the history of these codes go back until the 80s, the photochemistry and climate codes. So in the 1980s, Jim Casting, who's kind of a legend in our world, he created a photochemical model, and Kevin Zonley, he modified Jim Casting's code, and they published various papers in the 80s. And then Jim Casting also created a 1D climate model in old Fortran. And then for just years and years, these models were used for all sorts of publications. So like all sorts of classic calculations, like the habitable zone and the habitability of early Venus, the runaway greenhouse effects on Venus. That's what these codes did. And then I don't know the exact history of this, but something like 2015-ish, and maybe Ty would know this better than me. There, a couple of people, Mark Claire and Tigana Segura, Sean Goldman, and Ashley Palumbo, coupled these models together to make a code called Atmos. And people have used Atmos for the past decade for all sorts of cool projects. Also, a notable event was there's all sorts of different branches of Atmos going this way and that. And one of those branches was turned into the virtual planetary laboratory version. But there's all sorts of versions. And yeah, this is made by Andrew Lankowski. Okay, yeah. And then in late 2020, I made a Python wrapper to Atmos, and I called that PhotoChem. And then I was facing some challenges with my PhD project, and where I just couldn't do what I wanted. So I just took my understanding of how Atmos worked, and then I just rewrote it all from the ground up. But borrowing all sorts of ideas. Like there's still lots of concepts that are preserved, but hopefully none of the old code. No old Fortran 77. Yeah, and so that was in April 20th, 2021, midst of COVID, when I didn't know what to do with myself. And then yeah, I wrote PhotoChem for the last, I guess, 3 years. Or yeah. Yeah. So yeah. And the design of PhotoChem was inspired by Atmos, as I said, and a lot of different people. So to this date, I have no contributors. So it would be great if somebody would, help me, or if you wanted to find bugs and help me fix them, I would be appreciative. But obviously, it's a product of many different ideas and people. So Kevin Zonley, David Catling, a lot of different people, including Sukrit here. And I've messaged Ty a bunch, and he has graciously responded to my questions over the years. And yeah, it's inspired by Atmos. And then there's this chemical engineering tool called Cantera, and it's a great inspiration. They know what they're doing in chemical engineering. So yeah, and it's used in a number of publications so far. I think this is all of them. So some stuff I talked about yesterday on the early Earth and the origin of life, on K2-8b, some other exoplanets like TOI 270d, and a couple other papers that are accepted or in review. Yeah. Oh yeah, so tutorials. So that was end of intro. And yeah, at any point, just like, interrupt me and ask questions, or yeah, or indicate that you want to ask a question in some way. Yeah. So next step is we're gonna install the code, and then we're going to take a break after that. So does everybody have? We're gonna start by getting rid of this. Hate this thing. Okay, we're gonna start. Does everybody have this in? Oh, probably don't. You just have the website. Yeah. So everybody, well, at this point we don't need to do that, but we probably should. Okay, so I think at this point, if everybody could download this whole set of files, so you can. Does anybody have? Oh, who has a Windows computer here? Okay, one. Great. That's fine. So yeah, you can to download it, you can either put this command into a terminal, or you can go on to the website or into this guy here, and you can just click download zip, and it will download the zip, which you can unpack. And just download it and put it somewhere on your computer. So I'm going to go ahead and do that. So I'm going to go open a terminal. I'll make it really big. And I'll see. I'm going to go into my downloads. Oh, it's reasonably big, but like this. Oh, it's already here. I'll just and then I'll get rid of this one here. So yeah, just to leave that command up there, it looks like this, or you can just download it from GitHub. So who doesn't have it installed or downloaded? Great. Okay, so everybody has it. So in hopefully this is familiar to people. So this is Visual Studio Code. It's just a text editor. I'm sure you guys all use text editors for your coding things. And it's just showing I've opened up this folder in Visual Studio Code. And you don't necessarily need to do this, but I'm going to show you things on this program. You don't need Visual Studio Code. So we're going to go to number 2, and it has a README with some instructions. So it says, okay, you can install PhotoChem and the other packages needed for this workshop by following the steps below. So I want everybody well, let me walk through it first, and then essentially go ahead and try to do the install. So there are some special things needed for Windows computers. And we'll put that aside for the moment, but we'll come back to it. Okay, who does not have like the Conda package manager? Who does not have it on their computer? You don't. Okay. Does everybody else have Conda? Okay, so Antonin, there's this command right here, which hopefully you can copy paste into these 2 commands. And if you copy paste this into your terminal and run them, it's going to install the Conda command. And
I already have your version 0.4.5.
Oh, we're gonna do 0.6.3. Yeah, you'll manage. Okay. You're gonna update it. Yeah. Okay, and so if you have Conda, that's fine. And we'll come back to Windows in a moment, because this command is not going to work on Windows. But if you have a Mac or a Linux, this command is going to work. So if with Conda, you just are going to install PhotoChem with this command. So this is Conda create. You're going to create a workshop, an environment called workshop. This is like a fresh Python installation. And you're going to install PhotoChem 0.6.3 or 6.2. And you're also going to install Matplotlib and Jupyter for plotting and notebooks. And then you can activate that workshop and then run this command down at the bottom to make sure all the installation worked. So go ahead and go for that. For Windows, do you use Windows Subsystem for Linux?
No.
You've never used that. Okay. For Windows, there's a link here for how to use Windows Subsystem for Linux. Basically, it just allows you to use Linux in Windows, and unfortunately, Windows is hard, and I haven't made it. I mean, it in principle should be able to work on Windows, but it's not installable via Conda on Windows. Oh. Okay, yeah, so installation README, and then it says note for Windows. Oh, there you go. That link. I think there's a one command, so that command right there, go self-install. Did who's been able to get to this bottom command where you print Python and it gives you the version? You got it, and it says the right version. Nothing crashed. That would be. Actually, I should run this command. Before we do it. So this final command down here, it just should say Python version 0 or PhotoChem version 0.6.2. So I'll do the steps myself here. And let me know when that Windows subsystem finishes. Yeah. There we go. And then we're gonna do, I'll do the command here. Thinking, yeah, this is what you should see right there. Great. So yeah, so I think everybody, it's worked for everybody so far. Oh, yeah, okay. And I guess at this point, I mean, it has not been that long, so I don't know, our folks, once we get this sorted, you guys want to take a break or just charge forth to modern Earth? If there's any strong feelings for a break, let it be known. Otherwise, we'll move forward. Oh. Oh, so we won't hear, yeah. So now, if it's possible to open up Windows subsystem for the next.
Oh, okay.
Yeah.
That's what I was, that. So it's installed then and you want to open it.
Maybe just type, oh. Oh, try Bluetooth. That'd be great.
Okay.
Let me hit enter. It's on my old Windows laptop. W. Oh. We just have in WS.
Okay, I put the.
Okay, maybe we'll just stop there.
Oh.
Maybe quit Ubuntu and reopen it. See if you can. Yeah. Just type in Ubuntu. What time? Oh. So maybe try to close that and then open a command prompt, the normal command. And then just type in WSL and then navigation install it. Well, okay. Okay. I guess. Maybe, yeah, hopefully maybe you can Google around a bit. I'm no expert with Windows subsystem for Linux, but it should once it does work, it should be very straightforward. You open up one of those Ubuntu terminals if it works, and you basically just run you install Conda. You can do it with these commands right here. And you might need to get this curl command, and you can do that on Linux with this guy here, sudo apt-get install curl, and then you can run these two commands. And then after that, you can install PhotoChem. So hopefully, we'll come back to it at the break. But yeah. Okay, so charging forth, modern Earth, photochemistry. So at this point, everybody open up like a terminal like this. Make sure, or conda activate workshop like that. Make sure workshop is activated. And then type in the command Jupyter Notebook and run it. Wow, that's tiny. Okay. So, and then, oh, and I guess I just want to take a moment. So a lot of the codes that we use, right? A lot of the codes that we use they're sort of like you install this file system, you compile it and you run it, or something like that, right? You don't really install it on your system. It's just like you have some scripts that are hanging around. So I just want to like make it clear, like you have PhotoChem installed on your computer, but like where the heck is it? So I'm going to just take a moment to explain that before we jump into the Modern Earth tutorial. So move this guy down here, make him really big. So and you guys can all do this, or you can just watch. So you can do this command, or I don't think pip, but yeah, well, I'm gonna install pip real quick. But you don't have to do this. This is just for demonstration purposes as well. So if I do pip show PhotoChem, then it tells me stuff about PhotoChem. It's 0.6.2, blah, 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 blah. This is interesting. So it's in my computer, users, Nicholas, MombaForge, environments, workshop environment, library, Python, site packages. So if I open up this folder, and then I'm going to type in I'm going to go into the PhotoChem folder. This is what, oh, this looks so small, right? That's unfortunate. That's not that bad. Well, it's pretty small. Yeah, it's really small. But I can type, oh, it's just unfortunately small. So this is like when you install NumPy or any package on your computer, it's going to, with Conda, it's going to go to this file system and it's going to have some files describing that model. And this might look a little bit weird because since PhotoChem is written in Fortran, you get compiled binaries instead of like legitimate Python code. And so there's these files here, _climate, _equilibrate, _photochem. That is compiled code that you can't view the code in here. It's just ones and zeros that we will run. And then there's some supporting Python around all this. But this is where the code lives on your computer. When you installed PhotoChem, it also came with another package called PhotoChem Climate Data. This is a separate Conda package. And so for the photochemical model work, it needs all sorts of data like opacities, photolysis cross sections, these sorts of things. And that's where this resides. And so whenever you install PhotoChem, it will install a very specific version of the data that works with that model. There's no code in this package. It's just like files describing atmospheric properties. So here's PhotoChem climate data. The data, there's aerosol X sections, there's collision-induced absorption cross sections, Henry law coefficients, K distributions, Rayleigh scattering cross sections, some reactions, water continuum, and then photolysis cross sections. So just know that that's what happens when you punched in that command, conda install PhotoChem, you got these files on your computer. So let's do the Modern Earth tutorial. So, I already opened that up. So I have my Jupyter notebook. Does everybody have a notebook that looks like this? Oh.
So you mentioned about the binary files that are there.
Yeah.
If you want to just check out what how the code looks, is it possible? Is it
Yeah.
So folder files are those there in the folder, or
They're not in that folder. You need to look at like the PhotoChem GitHub repository. So like just to start, when you on CondaForge, so on Conda, you don't really upload your code you don't upload like the text files for your code. Conda will turn it into something that can be installed, but you can't really see what's happening. So to actually see the Fortran, you need to go on the PhotoChem GitHub repository, and then there's like a source directory and all the code is there. Yeah. So does anybody not have a notebook open that looks like this? Okay. And we're going to go into Modern Earth photochemistry, and we're then going to open the one that does not say completed. So open up this notebook by double clicking it, Modern Earth. Okay, so, and at this point, you can follow along, and if I leave you in the dust, and you're like, oh, I don't want to type notes, I just want to look at the completed notebook, that's absolutely fine. But you can follow along if you want to. But I'm gonna move forward without really waiting so much. So you're just, these are just really standard imports. So to use PhotoChem, you use it like any other Python package. So you import it, and you say from PhotoChem import Evo atmosphere. So Evo atmosphere is like the main. It's essentially you can think of it as a Python class, and it basically contains all the functionality of the photochemical model. So it contains all the functionality of the photochemical model. And if you want to look at, so all of the parts of PhotoChem have documentation strings. So if in Jupyter Notebook, if you put some variable and you put a question mark next to it and hit enter, then it will tell you about that variable like this. And so this says, this is a photochemical model which assumes no background gas. Once it's initialized, this class can integrate an atmosphere forward in time to a steady state. The model can also optionally self-consistently evolve climate for terrestrial planets. We're not going to talk about this terrestrial evolution climate stuff, just steady state modeling, mostly. And then it tells you how to initialize the model. So you have a bunch of parameters. So you have this mechanism file, a settings file, a flux file, an atmosphere.txt file, and then optionally, you can provide it with a directory that has a bunch of like data that the model needs to run. So we can just go through this. So we're going to initialize this code, this class. And the first thing we needed, well, let's put this back. So the first thing we needed was a reaction mechanism file. And if I'll just zoom back here, in this directory here, we have a couple different files in here. So there's in this input folder, there's a couple files, and those are going to be relevant. And then there's this reactions file right here. So the first argument is going to be Zonley Earth. And I'm going to talk about that now. So we're gonna feed it this file here. So is anybody who hasn't seen like a YAML file? Is that completely foreign to folks? Yeah. So it's just like a plain text file that has some structure to it. So it's kind of like a JSON file. And you can just think of these, if you're familiar with like Python lists and dictionaries, this is how you should think about these files. And so this is, in this file here, it's describing what I imagine is true for all atmospheres. So it's like the chemistry that should remain unchanged wherever you go in different planets. And so you say, okay, we have atoms, you got hydrogen, nitrogen, oxygen, carbon, and they have masses, and they also have redox. And then there's species that are made of these atoms. So if we look at like H2, it has a composition of 2 hydrogen atoms, and it has thermodynamic parameters. So there's different models to describe the thermodynamics of species, but this is the Showmate model. And these are some polynomial coefficients that describe like the Gibbs energies of hydrogen, which is important for reversing chemical reactions and for equilibrium calculations. So yeah, there's water. I mean, there's just a ton of familiar species. I don't know, there's 90, 100 different molecules. Where are we? So I'm just going to get to the end of the species here. There we are. So we got through all the species. Particles. So there are gas things, that was what we just looked at, and now there are particle things that fall out of the atmosphere. So water, condensed water, H2O aerosol. It's made of water. It has a density of 1 gram per centimeter cubed. Optical properties, I ignore clouds as optical properties. And it's formed from saturation, and its gas phase is water, vapor. And then this is the saturation vapor pressure properties of water. And, we can talk about this. This is essentially more or less a description of the thermodynamic properties of water vapor and of water ice. But yeah. And so there's a bunch of different particles: water or CO2, ice or fluid, sulfur, H2SO4, blah, 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 blah. And there's also some particles that form. So all these particles form from condensing. So they reach saturation, they condense and fall out of the atmosphere. Some particles form from reactions. So with hydrocarbons, we don't really, like in Titan's atmosphere or in the early Earth atmosphere, we can't model the things that should actually condense and form hydrocarbon hazes. They're too big of hydrocarbons. So we have to approximate their formation by a reaction that makes a big hydrocarbon that we say, oh, that's a particle. So that's what's going on right here. And then there's the chemical reactions. So there's a reaction equation, like H plus H plus a third body makes H2. There's different reaction types. The two main reaction types are fall-off reactions. So these are pressure-dependent reactions. And if you're interested in the details of this, we can talk about it. There's just standard sort of elementary reactions as well, where there's no third bodies. They're just simple elementary reactions. There's an arrow in each of these reactions. It goes both ways. It goes both ways. So when you have this arrow that goes both ways, when you initialize the code, it knows that it wants to reverse this reaction. So here you're specifying the rate coefficients to go in one direction, but it will reverse that using thermodynamic properties. If you get rid of that back arrow and only have that, then the code will know, oh, okay, I'm not supposed to reverse that reaction. Yeah. So that's this file. Oh, at the very end, we have photolysis reactions. So, UV photons break up molecules. So yeah. So that's the first input file. Moving on to the next one. So it says there's a settings file. Pass to the settings file. It's in YAML format. And we're going to do, in the input folder, there's this settings.yaml. I'm going to take a look at that guy. Input settings right here. So this is like setting up the particular planet of interest, and various other model parameters. And this would likely change, but from one atmosphere to the next. So one thing you need to specify is the grid of the atmosphere. So the bottom is at 0 centimeters and the top is at 10 to the 7 centimeters, or that's 100 kilometers. And then you have the number of vertical layers that you're discretizing the model with, the atmosphere with. And then there's all sorts of planet properties: planet mass, radius, surface albedo, solar zenith angle for radiative transfer calculations for computing photolysis rates. Hydrogen escape. Water is special and has all sorts of complications to it. And normally I turn off most of these things, and they're kind of holdovers from the old code. But so you can kind of ignore the complicated stuff that's happening here. So then there's settings for particles. Here I'm saying that the water vapor, it's going to condense at 0.5 relative humidity. And that's kind of what you need to reproduce modern Earth, roughly speaking. And then there's boundary conditions. So you say, well, how do I treat each molecule at the top and the bottom of the atmosphere? That's what's going on right here. So there's a bunch of different types of boundary conditions. So a critical one is a pressure boundary condition called press. And this is a surface pressure, a partial pressure of that gas in dynes per centimeter squared, which is, if you dynes per centimeter squared divided by 10 to the 6 gets you bars. So this is 270 bars of water. And you might be thinking, we don't have 270 bars of water in our atmosphere. That's right. But we have about that like reservoir of water in the ocean. So that's why. And in the model, if it won't let water go above its saturation vapor pressure. Yeah. Nitrogen on the modern Earth, oxygen 21% or 0.21 bars. Hydrogen, CO2, there's methane. So with methane, we specify a flux of the gas into the atmosphere. And this is in molecules per centimeter squared per second, classic photochemical unit. So yeah, that's this file. There's a bunch more settings, but that's the thrust of it. So the next file we need is a flux file, passed to the file describing the stellar flux. So its input, there's this file sunnow.txt. So we'll take a look at that. So here's how you this describes the UV flux for photolysis reactions. And this is like the UV flux at the top of the atmosphere. So if you were to add up all the energy and this spectrum here, this solar spectrum, it would add the energy would add to Earth's solar constant of 370 watts per meter squared. Yeah, these particular units, and it just, very simple file giving you the solar flux as a function of wavelength. From what? From what? Obtained from? I'm not sure. This is like the Atlas standard. I don't know. It's like it's a pretty old UV spectrum that folks have. Yeah, I'm not. Yeah. Yeah. Okay, last file. Atmosphere _txt, path to a file containing altitude, total number density, temperature, eddy diffusion, initial conditions of each gas, and the particle radii. So this is kind of a complicated file. But it's an inputs/atmosphere.txt, and here it is. So this is just a simple, giant, kind of a gihugic file that gives you a column for altitude. So when you initialize the model, you need to like kind of start with some atmosphere. And you say, this is like what I'm starting with. That's what this file is saying. It says we have altitudes in kilometers, these pressures in bars. These are densities in centimeters cubed, or molecules per centimeter cubed. And temperature is in Kelvin, and eddy diffusivity. So this is the vertical mixing in the atmosphere, right? That we need to assume in 1D models. We don't actually model convection. We need to parameterize it. And then there's all these rest of these are concentrations of gases or particles that the model is initialized with. So, and they're all volume mixing ratios, which is a bit confusing for particles, but yeah. So it's every single molecule in the atmosphere is described here in its initial concentration. So we have, well, not in reality, not every molecule, but every species we are modeling is described in that file. Yeah.
So you don't need to include every single species in the atmosphere file.
You don't need to. Oh, they don't need to. So you could just you could put in if you don't put in a molecule, then it'll assume there's none of it. Yeah. Or a very a negligible amount of it. Yeah. So you run this, I'm running the cell here, and it initializes the model. So it did that. It read all these files and it built a bunch of data objects, and And now it all lives in this object here called PC. How many are folks sort of generally familiar with like objects, object-oriented classes, this kind of thing? Yeah. So this PC object has a lot of variables attached to it that that and functions attached to it that describe the atmosphere and the chemistry of the atmosphere and everything. And so we can use it to do photochemistry. And so I want to start by just like helping us understand what is in this object here. So there's data like is stored in 3 different variables. Well, there's objects within the object. So pc.dat, this class contains data which rarely changes once the photochemical model has been initialized. So within pc.dat, there's lots of stuff that will only change if you reinitialize the code. An example is the species names. So if I run this variable, it gives you a list of all the species in the model. And this can only be changed if you like change the reactions file, for example, and reinitialize the code. And there's all sorts of stuff in here. You can always hit tab after you put a dot down in Jupyter Notebooks, and it'll give you all the stuff. Yeah, reaction equations, right? There's gajillions of reactions. What else is in here? Number of particles, 16. So yeah. So that's pc.dat. We'll leave them up. Yeah, and I guess another thing, this is a bit complicated, but if you want to know, obviously species names is a pretty good name for a variable, but not all the variables have great names. So you're like, what the heck is this thing? Like, what is NW, for example? What is that? Well, you can do, this is a bit complicated. You can import you need to do I'll just finish it first. So if I put a question mark in front of NW, it just tells me that this is an integer, which is very unhelpful. So you need to import the class, which this is an initialized version of this class, photochem data. You need to import it in this kind of wonky way and do photochem data.nw question. And then it tells you what it is, the number of wavelength bins and UV photolysis. So you can always do this to get more information about a variable. So the other important variable is pc.var. So this is this class contains data that can change between independent model integrations. So stuff like the temperature profile in the atmosphere. So this is an array of temperatures from the surface to the top of the atmosphere. And this resembles the modern Earth today. So there's that guy, and then there's pc.work. So this class contains data that changes during each step when integrating the photochemical model. So when we're gonna evolve these models towards steady state, and there's all sorts of stuff that changes here. Like the pressure in the atmosphere will change, the mean molecular weight, mu bar, that's mean molecular weight. But like the most critical one is the concentrations of gases. So for dumb reasons, this variable is called usol. I'm not really sure why. But this is a 2D array that has the number of species by the number of layers, and then each element in this array is a gas concentration in molecules per centimeter cubed. So we could do something like, get the index of H2O in the model, water vapor, and then we could look at the water vapor number density profile. and this is like, oh, this is confusing. These are molecules per centimeter cubed. Well, you can divide this by the density, the total number density in the atmosphere, and this gives you volume mixing ratios. So, you know, you don't have to remember all this. I'm just kind of giving you a sense for how this works. I'm gonna just jump over here momentarily and just peruse the notes. Blah, blah, blah. Oh, yeah. Okay. So we have all these gas concentrations. Let's just go ahead and plot up the atmosphere as it currently exists. So there is this file in this folder called utils.py, and it has this little function that just plots the atmosphere. So, you know, you don't need to know that, you know, you can look at it another time, but it'll just makes a plot of the atmosphere. So I'm going to import utils, and we're going to do utils dot plot atmosphere, and we feed it the PC object. And there's our atmosphere right here. So it's mixing ratio on the x-axis, pressure on the y-axis, and then different gases. So pretty. Oh, yeah. Right here. Yeah, I'll zoom in. Cool. Okay. Okay, so the next thing, I'm gonna just get myself in a better situation here. Reveal in Finder, and I'm gonna open this guy and just have him to the side. Okay. Okay, so now we've just we have this weird object that has all the photochemical information and that information in the atmosphere. But what we want to do with a photochemical model is compute steady state. So right, we want to make the model converge to the steady state. And so this is done by integrating the photochemical equations forward in time until stuff stops changing in the atmosphere. And we can do that very easily with this function, find steady state. Oh, crap. Yeah, we're gonna actually, there can be some weird printing business. So when we initialize the model here, let's turn off the printing. So we're going to reinitialize, or actually we don't need to reinitialize, but we're going to, before we call this function, we need to say pc.var.verbose is 0. Otherwise, we're going to get some pretty wonky printing. So I run that, this code's running, oh, and it returns a variable, and it says true. So the variable it returns is whether it's converged or not. And when this, when you run this function, it starts with the gas concentrations in this variable here. Oops, that we looked at earlier, pc.work.usol, and it integrates the model forward in time until you reach a steady state. And right now the model is basically at a steady state, so it takes no effort at all to get to one. So that's the one command way of getting to a steady state, but you can do this one step at a time as well. So there's this function attached to the model called initialized robust stepper. You feed it some initial conditions. Initial conditions. So this is the gas concentrations you're starting with. And you just paste this in. And when you do that, it sets up an integrator. And then you can integrate the model forward in time by doing pc.robust step. And it's going to return two variables, give up and converged. And we'll print these variables here. And it says, don't give up and it's not converged. So we initialized the integrator, it took one step, and it hasn't converged yet. And we can look at the model time. So basically all the information in this work variable is like all the stuff that's changing when you're doing these integrations. So the model time is we've made it to 10 to the minus 6 seconds after one step. It's not very, very long. And generally for rocky planets, the convergence criteria is we just integrate to about 3 billion years or something like that. And then that's when we say the model's at a steady state. So I can take another step, and the time advances a little bit. And I can take another step and another step, and you can see how time is just advancing slowly. And so we could, for the sake of, you know, showing what's actually happening, we can write a little function. So we had that function that, PC dot find steady state, but it's useful if you do this one step at a time thing and then plot the atmosphere as the integrator's chugging along. So we can write a function, a new one, that's find steady state, and it takes in that PC object, and it's going to do something like, utils.plot atmosphere. So it's going to plot the atmosphere. Well, we need this wonky thing. Clear output. Wait is true. We need that for whatever reason. And then, actually we need to do while true. So we're going to make an infinite loop here. And in this infinite loop, we're going to plot the atmosphere. And then we're going to take 10 integration steps. So give up. I'll just copy this. And then we're going to take 10 integration steps. If give up or converged, we're going to break this loop. And then we have to break again. So there's this infinite loop. We're going to make a plot of the atmosphere. We're going to take 10 integration steps. Along the way, we're going to see if we should give up or converge. We'll break this inner loop, and then we'll break this infinite loop. And we'll just return. And if you want to just not type all this out, this is somewhere in the other notebook. This is, yeah, I basically wrote this. Oh yeah, well, I forgot that line. But yeah, it's in this other notebook that says completed. So if you want to go to that notebook, you can just copy paste this. Actually forgot to show that and do this. Okay. So yeah, we need to first initialize the integrator. Then we need to plot the atmosphere and show it, then do a couple integration steps. So that's what I'm going to run down below here. Hopefully it works. Aha. So I'm going to zoom out a tiny. So this is plotting the atmosphere, and it's giving us time, and it already reached a steady state, but you saw for a moment there that it was integrating through time and plotting up the atmosphere. And this is very unexciting because nothing's changing the atmosphere. It's already at steady state, but let's change something. So, I'm going to set a lower boundary condition, set lower BC. We're going to change the methane boundary condition. And it's going to be BC type. So if you're like, oh, what is this function? What does it do, right? You can always do this. You can always put a question mark next to it, and it tells you this is the signature and these are what the variables do. But yeah, set lower boundary condition, BC type is going to be a flux. And then the flux is, this is going to be a small flux, 1E9 molecules per centimeter squared per second. So when we run that, then that will change the boundary condition, and then we can integrate to the new steady state, dictated by, and you can see that methane is in the brown line is changing concentration to accommodate for this new flux. Oh, and it reached a steady state already. But yeah. Is this generally making sense? Hopefully. If it's not, then shout out. Okay, so there's all sorts of other functionality attached to this object. So if we do PC dot tab, there's like a bunch of functions here. And, I'm not going to go through all of them, but one really useful one that I use all the time is this one, production and loss. So it basically tells you what chemistry is actually happening in the atmosphere and what matters. So we can feed it a gas, and then we have to feed it like the atmospheric compositions, and it's going to return a variable that I'm calling PL, production loss. And then we can look at like the production reactions. These are all the reactions that make methane in the atmosphere, and they're sorted from most important to least important. So we can look at integrated production, for example. This is like, so, these are the column production rates in molecules per centimeter squared per second for each of those different reactions. So this is a really useful thing if you're like, wow, what the heck is happening? Why is X, Y, or Z happening in my model? Then I use this function. I'm like, oh, what's happening with hydrogen? What's happening with methane? What's happening with CO2? And you can figure out like the different pathways, like what's actually occurring. Very useful. So there's two more components here. So in the notebook, it does more complicated things and plots the production and loss as a function of altitude, but we will skip over that. So one useful thing is we have this atmosphere at its new steady state, and we might be like, well, we want to we want to save this atmosphere for later. There's this function out to atmosphere txt. We'll just call it new. This will just take the information in the model and it'll print it to a text file. So if we go over here, there's this new text file, atmosphere new, and this has all the new gas concentrations that when we reach that new steady state. And we can use this file to reinitialize the code if we want, if we've reached a dramatically new atmosphere. And yeah, the last two things to cover very briefly before we take a break is first is so in terms of chemical reactions, so in here we use this file here, Zonle Earth. This is like my main reaction file, and I sometimes take a subset of these reactions. Maybe I use all the reactions. It depends on the problem, like for Titan, for example, chlorine is just not relevant because as far as I know, there's very little chlorine. Or sulfur, I don't know. I don't think, I get rid of some species that are not relevant. And of course, this reaction list isn't perfect. This came from Kevin Zonle, his 40-year career of chipping away at chemical reactions. This is just organized. But there's certainly mistakes, and there will certainly be updates to these chemical reactions. So you can always update any single one of them. And you can do that by just typing in a new reaction rate. And this, if you're familiar with kinetics, these are just very standard kinetics equations. So Arrhenius expression. So there's a rate coefficient, and then there's some temperature dependence. And it looks pretty standard. So here is like, this is the main Arrhenius. Looks kind of small, but this is a very standard expression, right? A t to the b exp of negative e sphère over t. Okay, next thing is there's a lot of data in the model. I showed you when we installed Viaconda, we got this other package called PhotoChem climate data. So we can import that from PhotoChem climate data, import data dir. So this is the directory on your computer where a lot of information is stored that's essential for the function of the model. And what you could do is you can just like if you want to change photolysis cross sections, right? I have sets of photolysis cross sections, and I made assumptions, and certainly they're not perfect. Maybe you want to change other data in the model. The way to do that is you're just going to copy this file, this whole directory, and then you're going to change parts of it. So I'm going to just jump over here, cheat a little bit. So this is basically going to make a new version of this data directory and just copy all of it to my local to this notebook. So here's a data copy. So now you could make changes in this, like, Rayleigh scattering cross sections. Maybe you want to change some of these values. And then you can just reinitialize the model pointing to that data. There's this, and that's the last optional value here. There's data dir, and we're going to just say data copy. So there's this optional variable when you initialize the code, data dir, and if you don't specify it, then it'll use the data that's installed on your system. But if you do specify, you can just give it a folder. So we could have changed all that data and you could initialize the model. Cool. So hopefully that concludes modern Earth, our very brief tour of modern Earth. So let's take a break, and then we'll return with some climate calculations. So yeah, and I guess at 3:30, yeah, in like 6 minutes.
Yeah, and I just closed the window because I wasn't able to get to it.
Oh, nice. I'm going to.
Yes, so we did that, and let's see, where do the shop.
So maybe start with,
So I did all of these.
oh, you did all of those?
Yes.
And they all work?
So I just need to do comma after the workshop. There you go. And then, yeah, I did that and that came out with like 6.2.
Wonderful. Okay.
But then how it gets to the loop?
Oh, yeah, because the wave tube is confusing. So, you need to go CD space slash, is it mount MT? See if that works. Okay. And CD and push tab. Oh, after a space. Maybe do ls after. Oh, C, there we go, we do CD, C,
Okay.
and then LS. CD users, with capital U. Then CD, like your username, we do LS. And where did you put them in your downloads or?
I'm gonna put B in
For all the files. Did you just download it, like as a zip to your downloads or?
I installed the.
Oh, wonderful. So now if you go to the top and, just click on right there and then go on that guy and then do down zip. And then go to terminal CD into downloads. And then you can type in Jupyter Notebook, right? I think it's fine. I think just you're gonna have to copy one of those local post iterations into your browser.
I'm not done with this.
Oh, you're gonna, oh, it worked. Oh, did it?
This is, what do you call it, no. So. We started this, I just had copied over with someone, but this hasn't compiled so far, it's still no.
Oh, start with the first command. Or wait, why?
What's this one does?
Um, maybe instead of for the. Yeah, it worked for me when I tried it, but
Okay.
I obviously it's. But you're so close. It's there.
Yeah.
Maybe Control C a bunch. A bunch of times. Yeah. And maybe we can just go through this. Open Jupyter. Or so. That we don't want that. Jupyter Notebook and Access. Maybe try this local host one. Is that what you did, or did you do that?
Yes.
Oh, you did local host.
Should I put this?
There's two URLs. Maybe try it. Oh, so you're gonna have to reset. Okay. And just hit the up arrow 2 times. Oh, maybe that once. And then, okay, HTTP/localhost. Do you have a notebook running in Anaconda, like in your normal Anaconda? Make sure turn off all your Anaconda with that. And then just copy that. And maybe restart the computer. Bunch of control C's. And then that.
Fantastic.
There we are. So now I'll try, yeah, go ahead and try that one and open up the computer. Let's just execute the first cell. Oh, it gives you, it looks different than mine, but that looks right.
Okay, great.
Yay.
Awesome, thank you.
Yeah. Okay. Climate modeling. Oh, we're missing. Oh. Okay, notebook 2. So just in my get rid of this one. And we're going to go to climate tutorial and open up climate tutorial. Okay. So within, right, to run a photochemical model, you need some estimate of climate. So there's a lot of, great climate models out there. And this code has a climate model for rocky planets specifically, and it's not the most incredible climate model out there. Clouds are hard. I don't really do clouds at the moment. But it probably gives you a reasonable pressure temperature profile and in many cases. And at the very least, I think it's really useful for me to just like experiment with habitable worlds and to sort of see what gas combinations might result in a habitable planet. Like what I'm going to show you today is, I don't know if you remember yesterday, I was talking about the habitability of K218b and how it doesn't work. This is exactly what I'm doing, is what I'm showing you today. So there's just some standard imports, and then the climate model, you import it by doing photochem.climate import this class, adiabat climate. Oh yeah, and if you want, this is a fancy thing, so it's multi-threaded, so you can run fast, you can change the number of threads. But yeah, you can leave that at 1, you can leave that at 4. It doesn't matter for this, but if you're going to do a bunch of calculations, then it's kind of nice to have it use a couple threads. I'm going to open up my completed version on the side, rid of that one. And yeah, we're going to do initialization. So to initialize this code, it's kind of like how you initialize the photochemical model. You give it, first we can just do the exact same thing, put a question mark. This class is a one-dimensional climate model. The code draws multi-species pseudo-adiabats upward, equation 1 in this paper by Graham. Connecting an assumed isothermal stratosphere. The model can also perform radiative transfer and do a nonlinear solve for the incoming solar radiation that balances the outgoing long-wave radiation. This is a little bit out of date. Anyway, it's a climate model. And you give it a couple files, a species file, a settings file, and a flux file. So some of these are going to look almost identical. Actually, all of them are going to look very, very similar. So I normally call the initialized version of this C. So we're going to put in the species file. So in this folder, I go in here. We're getting rid of modern Earth. We're going to climate. There's this input, which has all the input files we need. So input species. So this is going to look so similar to the one you saw earlier. There it is. Species looks like this. Atoms, species, The one difference is that the saturation properties are kind of located in a different information or different place, but this kind of looks like the reactions file you saw in the photochemical model. The one difference is that it's a lot shorter. There's just a couple species like oxygen, carbon monoxide, methane, H2, N2, CO2, H2O. So it's a lot shorter, but has the thermodynamic properties of all these different gases. So that's species. The next one is the settings. So settings file, we go to settings. This looks familiar, probably. So atmosphere grid, number of layers is 50. Planet properties, the mass, the radius, number of zenith angles. This is like how many different solar radiative transfer calculations you do, and then they're kind of averaged together. Surface albedo, and then this is important. This is the optical properties you specify. And so you specify separate. So for these climate calculations, there are two separate radiative transfer calculations that occur. There's an infrared calculation for infrared emission and solar radiative transfer for how much sunlight is being absorbed. And this uses, right, molecules absorb as a very complicated function of wavelength, and so people need to use approximations to that complicated absorption oftentimes. And a common method that people use is they use k-distributions, correlated k-distributions, and there's different ways of, this is a bunch of jargon, and I'm sure I know a lot of you know all about k-distributions. There are different ways of dealing with k-distributions, different assumptions you can make that can speed up the calculation or make the calculation slower. And so that's what this first parameters k method is saying, how are we going to deal with these k-distributions? And the bottom line is this random overlap resort rebin works really well most of the time. So you can just leave that. And then here you specify individual molecule opacities. And right now there's k-distribution. So this is line absorption, there's collision-induced absorption, and there's Rayleigh scattering. And so I could, turn off collision-induced absorption by just saying off. I could also specify explicitly the CIAs that I want. So CO2, CO2. But this would only have CO2, CO2 CIAs. So when you just say on, it will go out and look for in your data that we looked at earlier. It will look and try and use all of the opacities that it can. So this generally doesn't need to be changed. So last file is the stellar flux. So sunnow.txt. Sun, this looks exactly the same as the one you saw previously. This is just wavelength, nanometers, solar flux, watts per meter squared per nanometer. So we can initialize the model, reads all these files, creates this object, and there's, this is a bit simpler. So all the variables aren't like very deep into sub-objects. They're just like right on top. So there's all these are functions and variables relevant for running the model. So one thing you can, there are some sub-objects. So there's this C.RAD, that's like the radiative transfer part of the model. Oh, there's no docstring. So yeah. But one thing we can do is we can just print the opacities that are, oh, I need to run the function. Print the opacities that we have in the model. So like we said, use all the opacities you can, and what it went out and tried to find some, and now it tells you, oh, k-distributions are these, and the collision-induced absorption are these, and the Rayleigh scattering are these. So, this is useful because you could copy paste this back into your settings file and maybe get rid of a molecule if you want to know the effects, the radiative effects of a particular molecule. You could do that. Next step is, where are you? There you are. So yeah, we're now going to construct atmospheres. So Basically, a lot of the time I use like a simple version of this climate model that just kind of like constructs approximate climates that roughly are reasonable climates. And we're going to need, one of the inputs we're going to need is the gases, like the surface reservoir of gases. And what the code is going to do is try to distribute these gases in the atmosphere in a reasonable way. Because some molecules condense, water vapor, CO2 can condense. So we need we're going to need a NumPy array that is the length of all the species in the model. So I'm going to say numpy.ones, len, species names. So this is going to be an array of ones, and I'm going to make it a small number. So, and these are going to be surface pressures. And then right now I have an array of very small numbers, and I'm going to change some of the values. So for water vapor, for example, I'm going to find the index of water vapor. I'm going to change it to 270 bars. And then we're going to do the same thing with, say, N2. And we're going to say there's 1 bar of nitrogen. We're going to do the same thing with CO2 and say there's like 400, essentially 400 ppm of CO2. So this is sort of your generic habitable world. This is Earth without oxygen, more or less. But really, when we feed this into the model, it needs to be in pressure units of dynes per centimeter squared. So we just need to multiply these bars by 10 to the 6, and that'll get us an array of values. And this is sort of the input atmospheric composition, or sort of the input reservoirs. So next we need to, when we're constructing this atmosphere, we need to specify a surface temperature. So here I'll say 280 Kelvin. And we also need to specify tropopause temperature. So 200 Kelvin. And there's this function make profile. It takes in a surface. Well, let's see what it says. Takes in a surface temperature and the array of gas concentrations. And that just quickly constructs an atmosphere. So now there's all variables within the model that have been updated to reflect this constructed atmosphere. So for example, if I did C.T, this is the temperature profile in the model at each atmospheric layer, or C.P. This is dynes per centimeter squared, so I'll divide it by 6. But the surface pressure is close to a bar. The gas concentrations are in C.F sub I. This is kind of a big variable here. But we can, I'm going to go over here. I'm going to go to I'm going to just steal from the completed notebook. I'm going to steal this plotting routine. That's just going to, instead of just printing out those variables, it's going to make a plot of what's actually in the atmosphere. So this is familiar to what you saw before. There's pressure, there's gas concentrations, there's a temperature profile. We got nitrogen, we got CO2, and then we have water vapor that's saturated throughout the troposphere, and then it has a constant concentration up high. So this just like puts gases in the atmosphere. So there's a corresponding method that computes the radiative properties. It constructs the atmosphere, then it computes the radiative properties. So this function TOA fluxes. So it takes the same inputs, and it returns absorbed shortwave radiation and outgoing long wave radiation, I think, right? We can ask it. Let's double check by going. The first is the incoming shortwave, yeah. So we run this function and it constructs that atmosphere, then it does radiative transfer on it, and it gives you in return the fluxes at the top of the atmosphere. So if this was a stable climate, then these fluxes would be balanced. You know, this energy in would be equal to the energy out. It looks like they're not quite balanced. You know, you could try to manually balance them by punching in some other, oh yeah, I'm doing pretty good here. So it's 254, 257, you know, I could go up to 90. So you can see how you could try to manually balance those fluxes to get a stable climate. But there's also just a routine that does a nonlinear solve to balance these fluxes, and that's surface temperature. So you give it the gas concentrations and you give it a guess for the surface temperature. So we'll say 280 Kelvin, and it returns the balanced surface temperature. So it says at equilibrium, it's that you have the energy in equals energy out when the surface temperature is 290.8 Kelvin. We can confirm this by just, you know, punching in this surface temperature into the the TOA fluxes routine, and you'll see that these numbers are really close to the same. We can divide them almost the same. And so this is useful when you're like, okay, I want to, you know, what would Earth's climate be if we dumped, I don't know, 10 bars of hydrogen on top of it, you know? Then, well, I don't know if this is going to work very well, but oops. What if we, I'm going to guess the surface temperature would be 400. And then it says the surface temperature would be 482 Kelvin. So it gives you like a really quick estimate of like, oh, like, I mean, this is approximate though. This is, oh, yeah, maybe get rid of these x-axes. Oh yeah, in this case, you know, water vapor is filling the entire atmosphere essentially. And it's just like a adiabat going all the way up. So we could kind of change this by saying, you can change the top of the atmosphere. And maybe this would look a bit better. Oh, maybe go up to 7. So yeah, this is like a very water vapor filled atmosphere with a bunch of hydrogen, a quasi steady climate, more or less. So I'm going to return this to our much more normal atmosphere now of, you know, just much more like modern Earth. And we'll go back to 300. Yeah, wonderful. Okay, so those are approximate climates. Let's say you want to compute full radiative convective equilibrium. In reality, this is using rules of thumb to try to guesstimate the temperature structure, because generally there's convection low and then you have a roughly constant temperature profile up high, but in reality, it is not that simple. So let's go down here. Oh yeah, there's all sorts of stuff we can look at. So yeah, but we'll just skip over that. So I'm gonna just copy this because there's a chance I would put in. The problem is that solving for full radiative convective equilibrium is a hard problem. So these more simple climate models, they like work and you're gonna get convergence and it's great. But full radiative convective equilibrium is just hard. So I could easily put things into this model that will make everything blow up and produce a very weird answer. And so I'm just going to copy paste in what I know will work. So what do we got here? I put in some water, nitrogen, CO2. This actually looks exactly the same as what we had before. And then I'm changing the top of the atmosphere for radiative convective equilibrium, really low opacity, higher parts of the atmosphere that can cause the model to blow up. So we lower the atmosphere to be quite low, 10 to the minus 4 bar. And then there's all sorts of parameters having to do with trying to reach convergence with radiative convective equilibrium. But I'll just run this. Oh yeah, what we're gonna do is we're gonna get a guess for the temperature structure using this simple model that we talked about. And then we're gonna try and solve for full radiative convective equilibrium using this method, RCE. And this method takes in compute full radiative convective equilibrium. It takes in the array of pressures of each species, total surface, the surface pressure or temperature guess, the temperature layers guess in the atmosphere. So it's temperature as a function of altitude, and then the convecting pattern in the atmosphere. Yeah, there's a lot to talk about there. But you run this and it thinks for a while. It's probably printing something. Oh yeah. This might print in your notebook, and I guess for some reason it prints outside of my notebook, but this is just it chugging its way to trying to find a steady state. And it finds a steady state at with a surface temperature of 283 Kelvin. You can plot the atmosphere by copying that code. And oh yeah, much shorter atmosphere. Let's bring it down to. So you're right, this temperature structure now looks like it's more realistic. It's a full radiative convective equilibrium. So yeah, that is. Oh yeah, there's utility functions. Oh yeah, so in the example in the completed notebook, well, one really useful thing you can do here is that you can just, so I have this atmosphere in the model, we can call out to atmosphere txt. And I need to give it so you can output this pressure and temperature structure to a file that's easy to be read by the photochemical model. And you need to give it an eddy diffusion profile. The eddy diffusion isn't used in the climate model, but it will be used in the photochemical model. So right here, I'm just giving it a constant eddy diffusion profile of 10 to the 6 centimeter squared per second. So, we can look at this generated file. It has altitude, pressure, density, temperature, and this can easily be read by the photochemical model, and you can do photochemistry on top of this. And that's what we're going to do in the TRAPPIST-1E example. So that was super rapid, but hopefully that generally made sense. Just some simple climate calculations like modern Earth is. So next is TRAPPIST-1E. That was pretty short. Are we feeling a break, or should we just finish it off? Oh, absolutely. On anything. Yeah.
So I'm wondering how functions like surface temperature and maybe RCE actually achieve convergence. Is there some sort of tolerance parameter that you?
Yeah, there's a bunch. So with the surface temperature one, well, that one, there's basically there is a tolerance parameter, but it's not exposed and you can't change it. And I've never had a need to change that. With a radiative convective equilibrium, the full radiative convective equilibrium, there's a bunch of tolerance parameters. And so there'd be so this is an important one, max RCE it is. What does this say? Oh, it's an integer. Shoot. I need to say like that. Int, it's the maximum number of iterations in the RCE routine. It has a default value of 10 or something. Anyway, I just kind of crank it up if I want it to chug away for a bit. There is another, is it tall? You can find them. Oh, this is important. This is jargony and confusing, but to compute radiative convective equilibrium, it is treated, you need to compute the Jacobian of the equations describing the climate, and to estimate the Jacobian, you need to perturb, you need to do finite differencing to compute it, forward differencing. And so this is like a perturbation factor, and the convergence of the model generally works well with this number, but sometimes you need to tweak it. Or what else? There's one other important one. Not R tall. There's a tall. Haha, X tall RC. This is a it's a tolerance parameter that says how close should you get to radiative convective equilibrium before you're happy. This number seems to work. There's one other one that's really important, actually. Oh, this one, convective Newton step size. So normally when you solve for radiative convective equilibrium, like a lot of other models, they do this time stepping, and they like the photochemical model, you step, 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 and you do some convection, and then you're like, oh, the atmosphere stopped changing. And this model is a bit more, tries to just directly do a Newton solve, a root solve towards radiative convective equilibrium. But it's not like the most well-defined problem. And this is something that I need to write in a paper, a legitimate description somewhere. But the bottom line is like, this is kind of, and maybe you've heard of convective adjustment. This is something that people do to account for convection in 1D models. And this is kind of like a convective adjustment parameter. And if it's big, it's sort of, it's hard to describe. The bottom line is 0.1 works well, maybe 0.01 works well. But yeah, well, I guess if we look at this printing that's happening, what's happening in each of these iterations is that within this first 29 steps or whatever, it takes some convecting pattern in the atmosphere. And it says, well, we know that layers that are convecting, that energy is being transported via convection through those layers. But that whole chunk of convecting layers, we know that the radiative energy in and out of those chunks of layers, that energy should be balanced. So it takes some convecting pattern, and then it solves for radiative equilibrium with that convecting pattern. And then what it does is it checks to see, are all the layers stable to convection, or should a layer that is convecting be radiative? And so then it changes things and it recomputes that equilibrium. And then it does it enough times until it reaches a point where it's, you stop changing the convecting pattern. It's hard to explain, but yeah. Does that sort of make sense? Yeah. Yeah. Cool. Okay, to TRAPPIST-1E, or should we, break? Or okay, if we should break, just let me know and we shall. Come on, I can't see it because that guy. Oh yeah, and one thing is, there's a bunch of other tutorials that I made that I was like, oh yeah, these things are interesting, but we're not going to talk about. So, oh, see you later. Yeah. If you're interested in, like we're not going to talk about gas giants and brown dwarfs, for example, but I know people here model brown dwarfs, so and gas-rich planets. So there's a tutorial for how to do that. Reproducing the habitable zone, that's here. Installing from source. So if you want to like compile all the code and change the Fortran, that's described here. And changing the cross sections, the model data, that's described here. And then this is just another example for the Archean Earth. So for the TRAPPIST-1E, it is not a demo situation. It's like this notebook is like a problem, and it's got 4 questions, and hopefully it gives you a lot of the code that you need to solve this problem. But the notion is that you can go through it, and we can go through it roughly independently, and then just try to simulate the climate and the photochemistry of TRAPPIST-1E's atmosphere. And so yeah, the 4 questions that we're going to try and tackle is, first we're going to assume TRAPPIST-1E is inhabited by methane producing microbes and has an atmosphere similar to the Earth's 3 billion years ago. So it's mostly got nitrogen, CO2, and methane. And so the goal is to create photochemical and climate models of the scenario and answer these questions. So what's the global average surface temperature for your assumed atmospheric composition? what's the surface methane flux required to sustain whatever methane concentration you prescribe, and how does it compare to the modern Earth's? What is the main destruction path for methane in the atmosphere? What is the hydrocarbon haze production rate in grams per centimeter squared per second? And how does it compare to Titans? So hopefully we can all just chip away at it, and we'll see where it goes. So yeah. And yeah, if you're not interested in TRAPPIST 20 and want to talk about like brown dwarfs or something, then just let me know, and we can also take this time, like any one of you want to do that, happy to do that as well. Uh-oh. Oh no, it worked. Yeah. In reality, there's like not that many things you need to punch in. So did anybody just punch in some numbers yet? And you did, yeah. Did it blow up or did it produce something reasonable? Oh, that's good. Nice. Oh, yeah. Yeah, see you, Lily, yeah. And yeah. At this point, did you get through it all? Didn't model blow up. Oh. Looks like, there could be, oh, no, you're getting there, right? This is a cumulative time, but sometimes it resets, yeah, because it's stuck. And it tries to restart. Oh. Let me see. I mean, it may never get there if it's pretty long. I mean, inputs may be very reasonable. Good. Wait, what's the bars, 20 minus 3. What is the planet going to go? And then is it? One thing, this is obviously, I'm sure. Yeah, yeah, you do. So converging atmospheres can be a problem, obviously. So maybe hit the stop button at the top. Right, so it's, here we go. Okay, good. So maybe there's all sorts of settings. Oh yeah, the tolerance, that's important. So make a new cell beneath that cell. Plus. Pop that. Oh, you made a new cell. And then there's this variable pc.bar auto diff. So you know how like when you compute the Jacobian, like the Jacobian needs to be given to advance the time step. So there's two different ways that this will compute the Jacobian. One is this fancy method that sometimes works and sometimes doesn't. Right now it's this reactive, so it's we put true, variable true, and then execute that cell, and then just restart the run the new cell and stuff. So you can, and then the other thing to trust is this absolute tolerance, which is something I should have explained. Oh, yeah, you know it. Yes, yes. So anything like the integrator. Oh, it did it. So yeah, I should explain that other here. But the atoll is if the concentration is less than that, then it won't. It's not really factored into the time stepping decision. Yeah, yeah, it's like kind of, you don't worry about concentration. It just, if the model can get itself to, right now the model's at, 10 to the 17 seconds. So that's like 3 billion years. So if we can integrate down to or is that 3 billion? Anyway, it's a couple billion years. And if it gets there, does that help? Yeah, that's it. I do that. So for gas-rich planets, I can never get to 10 to the 17 seconds. So, I just do. Well, that was the last time it's plotted. So you could print PC dot WR dot. This would be. So it made it just past 10 seconds. But it didn't, it made it there and it didn't pop yet. Did any other model blow up? It's chugging away. It could be. This is a challenge, a constant challenge, especially when you're starting with a fresh atmosphere that, where, yeah, this one looks like it want to make it. So what would you do? Let's see, is that like. So yeah, you could you could change. There's a couple of parameters to change that help. One of them is the absolute tolerance ratio, and then the other one is how the algorithms are treated for and so you can maybe stop integration, stop time. And then just make a new cell above for all that.
Is it sorted by like most prevalence, least prevalence, or production most prevalence?
It's it's sorted by the integrated thing. So yeah, and then you see dot WRP. Or sorry, you see dot positive. No. And then you and then execute that time. And then execute. Oh. Oh. Yeah, you actually. Oh. That's the thing. You can be finicky at times. Yeah. I mean, in theory, that auditive thing should be like, it's like this really fancy way to do this, which would make it right. So anyway, so now.
Thank you.
Yeah. Did yours get to extend state?
Yeah, I think so after a bunch of generations.
It's just what's that?
I said it's not stuff. It's generacy.
Yeah, probably haven't. So one thing to try, that we tried it with Brave, was you just stop integration. And then make a new cell above somewhere, yeah. And then QC dot bar. And then run that guy, and then so. And maybe. time, you can see it's not really advancing very fast. Oh, never mind. And then there's the switch. 273.
Okay. CC7, but
Oh, that's great.
that was.
Oh, yeah. Yeah, I guess that already is the way to go for this. It can be finicky.
So, production capture.
Yeah. 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 And then they do the yeah. Oh, nice. Oh, yeah. It's weird. Sometimes I get the same number roughly for Titan, and sometimes I get way less. Who's the other guy? Yeah, I'll do 1 bar. And 1 bar. 106. Like that. Oops. Cool. So just arbitrarily, I put in a bar of nitrogen, bar of CO2. I think, right, that's a lot more than probably was in the Archean, but why not? 1,000 ppm or 1,000 times 10⁻⁶ bar. And this gets me a hot climate of like, surface temperatures like 320 Kelvin, but still habitable. There's still liquid water down there. And then this is my model didn't quite converge, but yeah, one thing that, so I think everybody went through it, and other photochemical modelers in the room can attest that finding steady states can be challenging at times, and because the photochemical equations is a really big system of nonlinear equations, so it's hard to find the steady state. And there's kind of 2 parameters that I just play around with sometimes to try and get me there. So ATOL is an absolute tolerance of integration. So it basically says if there's a gas concentration less than this value, then the integrator kind of doesn't care about it. And you don't want this number to be too big. Like if I had it 10⁻⁻10, then it would be ignoring a bunch of species that it should keep track of in the integration. But if I had it too small, like 10⁻⁵, then it would be keeping track of these really trace species, and just the model would have a really hard time advancing. So this number 10⁻⁻23 is like kind of works most of the time, but to be honest, it does depend on like the atmosphere. If you're modeling a really hot atmosphere, it changes, or a cold atmosphere, everything. And then this other parameter is autodiff. Is anybody heard of automatic differentiation, like the technique? Yeah, you've heard of it. Yeah. It's basically like this. It's the coolest thing ever from a nerdy math perspective, but it's like this really accurate way of computing derivatives. Like it's literally accurate to machine precision. So it's basically perfect. So that's one technique for computing derivatives relevant to integration. But then the default method isn't autodiff. It's using finite differences. Long story short is sometimes it's better to use the autodiff and sometimes it isn't. And you would think that autodiff would always be better, but it's not. But in this case, it seemed to work really well. Yeah, and I got to a convergence. And you guys probably use this function gas fluxes, and you can look at the methane flux at the surface, which if I divide it by modern Earth's methane flux, in my case, I get a methane flux of 4x modern Earth's. So that was the question 2. And then 3 and 4, main destruction path for methane. We did that production and loss function. It goes CH4, PC.work, aerosol, PL dot production. Well, we'll run this first. And then production reaction. That's the main production. And then main loss. So in my atmosphere, the production is going to be way small. Oh, where's, yeah.
Are these all the reactions that are listed in production reaction? The reaction on how efficient they are in formula.
Yeah, they're in order of importance. Yeah, so I'll just steal something from the finished notebook. It'll make it more clear. Completed, and there is, oh well, maybe not really, but sort of. Yeah, we can. Oh yeah, this does make it more clear. So this is just printing out does production and loss and looks at the loss, and then it computes the integrated loss. This is over the entire atmospheric column, molecules per centimeter squared per second that is destroying methane. So I can like print, instead of 5, I can do 20 loss mechanisms, and you can see how these values are sorted. And some of these just so totally unimportant. So, and in some cases, right, methane, photolysis is the most important. Some cases, it's like modern Earth, and OH is the main destruction path. And then the last one, I had this little function, haze production rate. And in this case, there's like no haze production rate compared to Titan. Titan's was like 1e minus 14. So I get a factor of 70 million less than Titan. So the haze production rate stuff is like questionable. Like when I model Titan's atmosphere, I can get the haze production right. So I'm like, oh, that's pretty good. But then when you go to these exoplanets, they're very different than Titan. So I don't know if that works very well or not. I mean, it does make some sense because you look at, well, let's look at this atmosphere. I don't know, it's hotter, maybe cooler atmospheres will have better haze production rates. I could imagine that. There's more water vapor in my upper atmosphere than in other cases. So yeah, that's like the basics of the model. And yeah, we have, I'm not sure what, we have a couple minutes, and of these final topics here, I'm kind of thinking that maybe the most interesting thing to talk about might be in like compiling the code, if you were interested in that, or if there's something else that we're interested in taking a look at, or you speak now, or we can just try to each compile the code. I'm sure it will fail spectacularly, but it should be possible for each of us to do that, and then you could change the Fortran and there are some reasons why you would want to do that. Like, there's assumptions and some constants that could be changed. So yeah, let's give that a whirl. So for this, compiling the code is a complicated thing, unfortunately, and that's why I put it on Conda Forge, because Conda just it compiles it all and puts it on a server, and then you can and then I can install it very easily, and other people can as well. So I'm gonna just do preview here. So to compile it, you need a bunch of different stuff. So this is to compile it, I just make a whole new Conda environment. You don't necessarily have to, but this is going to make a Conda environment that has all the stuff you need. So I'm gonna just open up a new terminal, cd into installing from source, and I'm gonna make it bigger. And then we're going to do make this environment with all these packages. So while that's chugging away, the main things is you need the data to make the model run. That's a dependency. You need a bunch of packages to, like, when the code runs, these things are necessary. To build the model, you need all sorts of things. The most important is a Fortran and C compiler. So that's Clang and G-Fortran in this case. But you need all these other guys to do various things under the hood. And then the rest of these aren't actually needed. I don't know why I added them, but these sets here, I'll say yes. And next this is the GitHub. We're gonna just clone the PhotoChem GitHub and get the source code so we can compile it. So yeah, to do that. And then okay. And then there's all sorts of junk that needs to happen so that, like, the right compilers are found by everything. There's also some other special, these commands are is like when you made this Conda environment, installed a bunch of libraries, and the code needs to be able to find those libraries and link to them. So I'm gonna just run a bunch of all these commands to make everything work. And this looks like a lot, which it kind of is. And this is just to make sure everything works like the first time you do it. In reality, I don't need to do all these things. Most of the time, the code is able to find the right libraries and stuff like that. And I can literally just run this final command. Because I already have a C and Fortran compiler on my system. I just need to run this very last command here that does all the compiling. But all this is just make sure that everything is properly found. So then you run this guy, and it it does it compiles everything. And I'm gonna open up installing, or let's open up this guy. So I'm opening, oh, whoopsie. It's not good. So this is the GitHub that we just downloaded, the source code. And all the source code's in here, so it's compiling all of it. Yeah, so it's chipping away. So at this point, this should work. And now you can change the Fortran. So, if you're like, I don't know what you would change, equations as an example. There's assumptions in here, like, let's change something. The default binary diffusion parameter as an example. You could change a number in here. And then, so this worked, it says installed. So you just, it all compiled and installed. And so now you could use that version of the model, but I changed the code. So now I can run that install command and it will go and just compile the files that you changed and it will rebuild everything and install it. So in this way, you could imagine like you can make changes to the Fortran and, change the code, etc. Did anybody try to make that happen or? Oh, you did? Or no, you just questioned, yeah.
But no edit, but somehow it doesn't find the data.
Oh, it does it, or the data folder?
Yeah, the data. Well, yeah, I kind of decided, but to start with that. But yeah, in the end, the install looked like it was working.
Yeah.
But when trying to run with it, then we would find the data. But also I was not aware that you had this tutorial when I started trying.
Oh.
But I don't see from the tutorial where it would find the data.
Oh, in here, so,
Like it's a dependency, but in the story.
oh, so when you go up a little bit, so like that says create blah, blah, blah.
But it's nowhere outside of that point.
Oh, it is, well, it is, you could just, download it off GitHub, that's also on GitHub. So yeah, it's just, I can't find tabs. But, you go here, it's somewhere in here. Yeah, there's a GitHub. So this repository contains data for PhotoChem. So you could, yeah, you could just install this directly. So you could either install it from CondaForge, or you could do something like this where you like downloaded it like that, and you go Mamba activate test. So that's and then you could just do a pip install, and it says it uninstalled PhotoChem climate data, and then it reinstalled it. But anyway, you can install it via Conda, or you can go on to GitHub explicitly like that. Yeah. Cool. Yeah, any how are we feeling? Are we, this has been quite a long time, 2 hours and 40 minutes, so I'm fine if you guys are ready to call it.
Is there online documentation tutorial for PhotoChem or?
That's what you got, because the challenge is that I want to make legitimate documentation, like a read the docs or something like that. But that like there's this challenging balance between like documenting a thing and then making it easy to change it, because like it's hard enough just to change things and make everything consistent, and everything work. If you want to add a new feature, then. And so the challenge is if I've been, I've just failed making documentation so far, because then if I change the code, then I need to change the documentation, and it makes it harder for me to change things. But on the list of things to do is to make a legitimate, like, read the docs. And that's why this tutorial is pinned specifically to like a version of the code, because it's very possible that, there's a bug, I'm sure, or who knows what, something will change in the model. And so then we'll come back and you try to use a different version of the model to run this tutorial and it wouldn't work, because we changed things. And this is just the nature, right? It's, you got to have versions, and that's what I do. Like when I write a paper or do a project, I just like say, okay, this is my version for this project and I'm going to use it. But then I may, stop doing the project for a moment and start, work on the model a little bit and update it. But still, I'll go back and use that older version for that particular project. But anyway, documentation, I need to, that needs to be made. Definitely the most comprehensive documentation I have is these tutorials for this workshop. Like there's quite a bit, here. Like, does anybody do like gas giants? Yeah, Ty does gas giants. Yeah, like here, well, I mean, most of you may not be interested in this, but this like reproduces some WAS39b photochemical calculations, which was recently a thing that came up from James Webb. And then another fun thing to do is like reproduce the habitable zone, like distances from the star that you can have surface water. So this reproduces like there's a famous paper by Ravi Koparapu back in 2013, reproduces that. I guess, and then this gives you a sense for how to change the model data. So for example, Sucrit, I know, has like maybe new photolysis cross sections for species. And this could give you a sense for it tells you how to change those kinds of things. In terms of like documentation, the best thing I have done so far is that almost all the variables have documentation strings. And we saw those when you put like the question mark. And that would be the way to look at those variables, is with the question mark. In reality, those strings are in all the Python wrapper to the code, which is honestly a little bit complicated to look at. But we can open up, this is like the main wrapper, and this is the doc string that we saw here, and each of the functions is has a document string is associated with it. So you can look through that, but yeah, I need to make like a nice read the docs. But I mean, not so many of us fail to make good documentation, right? Like just as an excuse, like my advisor, Natasha, this is her beautiful, she has a radiative transfer code, and she's got this beautiful called Picasso. And she's got this beautiful documentation that you've probably seen these kind of pages before. And this is the goal. I want to get here someday. But yeah. But yeah. Like the whole vertical column. Through the whole column. No. You cannot do that. You can only fix the surface concentration. Yeah. Is that something you can do in MEAC? Is fix the whole? Oh, really? Or is it vertically constant, or do you specify some?
Yeah.
Interesting. Yeah. So that would be a thing to add, right? Like you could imagine how that could be done. You could have some function like instead of production and loss, you could say fix gas concentration, some function that goes in and changes the relevant parameters, and you give it some concentration as a function of altitude. And so yeah, you cannot do that at this moment, but it wouldn't be the hardest thing in the world to make that happen. Yeah. Any other, how does this, I've never used MEAC. Is this sort of like this, or I've seen some of the input files is all. Yeah.
If you go to some different periods.
Yeah.
Yeah. I was actually trying to run the same thing on both the models.
Oh, yeah.
But not able to go completely to it again. Now I will. So
Yeah, yeah.
that's something.
Cool. Nice. Yeah. No, I've only seen the input files. Is all, but yeah. MIAC is kept secret, right? More or less. Yeah. Cool. Yeah, any other final thoughts before we call it a day? Yeah, let's call it a day. Cool. Thank you guys so much. I really appreciate